Q is times L. So now H is reduced by half, so but the Q remains the same. So we know the Q is 10 to the 6th watts per meter cube. We have 250, and we're trying to estimate what this wall temperature would be. Because that's the fundamental variation between this problem, between this section and the previous sections is, because the heat transfer coefficient is lower, your wall temperature will be different. So T wall and T infinity remains the same, which is 20 degrees Celsius, that's the ambient temperature here. Length also remains the same, which is 50 millimeters. So when you substitute these equations, your wall temperature turns out to be 220 degrees Celsius. Now, if we go back to our equation here and look up the equations for each of these constants, A should be equal to the wall temperature, which is 220 degrees Celsius. B is Q dot L by K. Remember, the Q did not change in this problem, it's the same, so your coefficient should remain the same. And so it'll continue to remain 10 to the 4th degrees Celsius per meter cube, meter. And C, which is negative Q dot by 2K, will remain 10 to the 5th, negative 10 to the 5th degrees Celsius per meter squared. So we do have these constants. What is to note is the slopes, the slope dt by dx, it's a function of only b, c, and x. In both cases, b, c, and x remain the same, and therefore the slope of the new temperature profile for this condition where the heat transfer coefficient is halved should remain the same as the one before. And so we should expect a similar slope, just that the starting point would be at 220 degrees Celsius, which is given by the wall temperature here, as opposed to the 120 degrees Celsius that we were previously seeing. So let's assume this is 220. And it should follow approximately the same slope. It's about the same. It should follow the same slope. The graph is approximately the same. This temperature here is 470 degrees Celsius. So that's part C. Now we're looking at the final part, which is where this heat generated term here, that's half. The heat transfer coefficient is back to 500 watts per meter squared Kelvin. And we're trying to find out what the temperature profile would be. So in other words, what these constants A, B, C would be and how they will compare with the previous temperature profiles. So we again go back to the equation number 1. I can erase all this here. So we are back to Q dot is HT wall minus T infinity by length or the thickness of the wall. You substitute 500 here, and you substitute 10 to the 6th by 2, 1/2 of it. We're trying to estimate what this wall temperature would be, because that will tell us what this coefficient A is here in the problem. Intuitively, the heat generated term is, the heat generation rate has decreased, and your heat transfer coefficient remains the same. So you expect the wall temperature to reduce, and that's basically what happens. When you substitute the values here, the relevant values here, the wall temperature is estimated to be 70 degrees Celsius. It was previously here 120 when in the first baseline case, and then when the heat transfer coefficient was halved, it was 220. In this case, where the heat transfer coefficient is the same, but the heat generation rate is reduced, the wall temperature reduces to 70 degrees Celsius. Now that is our A in this equation, so we already know that. This time B and C will change because the heat generation term has changed. And the equations for B, which is QL by K, and C, which is negative Q dot by 2K, they turn out to be 5 into 10 to the third and negative 5 into 10 to the fourth. So these values have changed, and so we expect the slope, or both the dt by dx and the d squared t by dx squared terms, they'll change. And so the temperature profile would be a lot different from, will have a different slope. It will generally be the same, but it will have a different slope. So we're looking at 70 degrees Celsius. Let's mark this as 70 degrees Celsius. And it is expected to be, it's not supposed to cross over. It's supposed to be somewhat like this. So this is case 3, where the highest temperature here would be closer to the 190 mark. So we have right now considered 3 different cases. We've looked at the influence of the heat transfer coefficient on the wall. We've also looked at the influence of the heat generation term inside the wall. As you increase the heat transfer coefficient, you expect the wall temperature to decrease, which is what we see in between cases 1 and 2. If you decrease the heat generation term, we expect the wall temperature to go down, as well as the slopes to be less intense, because these coefficients are lower, and the temperature profile will also change. What has to be noted though is that the boundary conditions will still remain the same. That is that this tip is adiabatic, and temperature at the wall will be the wall temperature, which is measured. Thank you.